We have already studied speed control of DC motors. In this lecture I will take some numericals, and with the help, for better understanding, with the help of numerical we will try to observe what effects we have studied in the speed control of DC motor. So I am taking a numerical here. Suppose this is a DC series motor where field resistance plus armature resistance equal to 5 ohm. Since the field winding is connected in series with the armature winding, so we can combine field resistance and armature resistance, and let's say this is 5 ohm. This DC series motor is connected to a 220 volt supply, and it is running at 1000 RPM. It is driving certain load. There will be some load torque, and it takes 5 ampere current. In this steady state, this situation is given. What is the meaning of a steady state? In a steady state, the speed of for any machine, if the machine runs in a steady state, the speed will be constant. In each problem of DC machine, we have to solve it for a steady state condition only. If we talk about transient, we study transient only in synchronous machine, where we have problem of stability. So we need to study transient in synchronous machine only. In all other machine, if we are given a problem, that problem will be asked in a steady state condition only. Okay, so in a steady state, speed will be constant. The net torque on the machine will be 0. If you will make some change to this machine, initially there will be some transient. So in that transient condition, normally question is not asked. So if you make some change to this machine, suppose you suddenly increase or decrease resistance with the help of rheostat, initially there will be some transient. In that transient condition, speed may vary, but again after transient state, after some time, the speed will again become constant, and we will again have a steady state condition. Okay, so this is the initial situation. Now suppose we have to control the speed by varying this resistance. Here we may have a rheostat. There may be field resistance will be there, and there will be armature resistance. Instead of showing here, I am showing here. So the total resistance, initial total resistance is 5 ohm, and the speed is required to brought down to 800 RPM with the help of armature resistance control. So how it may be done, whether we should increase this resistance or decrease this resistance. So first we will write equation for this DC machine. We have terminal voltage. Here we will have armature voltage or generated voltage. So we will have Vt minus Ia into R. This R is total resistance, field resistance plus armature resistance. This is equal to armature voltage, and this will be equal to K phi into omega. This is one equation, and other equation is, this is voltage equation. Other equation is T equal to K phi into armature current. Now suppose you want to decrease the speed. So to decrease the speed, if only the question is whether you should increase or decrease this resistance. So if you want to decrease the speed, omega has to decrease the speed, armature generated voltage has to be decreased, and when it will decrease, Vt is fixed when you increase the resistance. But in this relation, phi is also not constant. Okay, so this is one consideration. Another consideration is you have to decrease the speed, but nothing is said about the load torque. Okay, you may increase or decrease this resistance, but nothing is said about the load torque. Means load torque is constant. So you will increase or decrease the resistance. There will be some change in the speed, but again in the steady state, let's say speed will become 800 rpm. But again in a steady state, the net torque on the motor should be 0 to maintain constant speed. So initially torque was k phi into I. After, when again the steady state will be reached, the new torque will be k phi new into armature current, the new value of armature current. And what is condition here? K phi old. Okay, and what is IA? IA is 5 ampere. Now if we talk about DC series motor, the flux here, in case of DC series motor, armature current is equal to field current, and if we neglect the saturation, the field flux is directly proportional to IF. IF is equal to IA. So the field flux is directly proportional to armature current. Now if we equate the two torques, because the load torque is constant, so in both the conditions, in a steady state, the machine torque will be same. So if we equate the two torques, k phi into 5 ampere will be equal to k phi new into IA new. Now if you see this quantity, what is k phi into 5? Phi is directly proportional to armature current, so this can be written as k into another constant k1 into IA, the previous value of armature current, into 5. What is the previous value of armature current? Here what we will write, k into k1, the new value of flux will be directly proportional to new value of armature current. So this will be k, phi will be k1 into new value of armature current and into new value of armature current, so we will have a square. So we will write k into 5 square equal to this. So we will have is equal to 5 only. So what we observe here, even if you change the resistance, if the load torque is same, even in new condition, the armature current will be equal to the previous value of armature current. If I make it in a simpler manner, if you see the torque, this has to be constant because load is constant. Torque is equal to k phi into armature current, and phi is directly proportional to armature current, or we will write torque is directly proportional to phi into IA, and phi is directly proportional to IA, so torque will be directly proportional to IA square. So if in initial and final condition torque is same, then IA will be constant. So I will take, here we have first condition, here we have second condition. Speed equal to 1000 rpm, here speed equal to 800 rpm. Here we have IA equal to 5 ampere. Here also we have IA equal to 5 ampere. Supply voltage is 220 volt. Here also supply voltage is 220 volt. what is the value of generated voltage here? Armature voltage 220 minus Ia into R. Ia is 5, total resistance is 5. This is 195 volt. What will be the value of EA here? EA equal to 220 volt minus Ia is 5, and let's say new value of total resistance is R. So here we will have this generated voltage, and generated voltage is equal to K phi into omega, and here we will have, let's say this is initial condition. This in initial condition flux was phi 1 and omega is omega 1, and in final condition we have flux is phi 2 and we have this omega 2. Now if we talk about generated voltage or armature voltage, armature voltage is K phi into omega, and phi is directly proportional to armature current. So in both the conditions armature current is same, so phi will be same. So if you compare the previous and final condition, K phi will be a constant, so EA will be directly proportional to omega, or we can say that EA will be directly proportional to speed. So in first condition EA is, or we can write it as EA1 divided by EA2 will be N1 by N2. N1 is 1000, N2 is 800. EA1 is 195, this is 195 divided by EA2 is 220 minus 5R. So if we solve it, this will be 5. So if we solve it, we will get R equal to 12.8 ohm. So what is the extra increase in resistance? Increase in resistance will be 12.8 ohm minus the previous resistance is 5. We will have 7.8 ohm external resistance. So there are certain things you can remember in case of DC machine or in case of any machine. If you will increase the resistance, the speed will decrease. If everything is constant, if you will increase the resistance, the speed will decrease. I am writing certain points which are correct in almost every cases. What I have observed, in any case, if you will increase the speed will, if you will increase the resistance, armature resistance, whether it is DC series motor, DC shunt motor, or separately excited motor, even in case of 3-phase induction motor, if you will increase the resistance, speed will go down, speed will decrease. If you will increase load torque, speed will decrease. If you will increase the load, whether it is electrical load or it is mechanical load, electrical or mechanical, if you are increasing the load, armature current will increase. Now in the same question we will again make some changes. In the first condition what we had, supply voltage equal to 220 volt, armature current equal to 5 ampere, let's say load torque equal to T, total resistance was 5 ohm, speed equal to 1000 rpm. In the second case, we have supply voltage 200 volt, torque is constant, hence armature current is constant, load torque is T, resistance is increased to 12.8 ohm, then speed decreases to 800 rpm. Now in the third case, what is done? Up to second case, what you observed, if you will increase the armature resistance, speed will decrease. Similarly, if you will decrease the resistance, if you will decrease the armature resistance, speed will increase. Now in the third case, in first to second case, we kept the load torque constant, we varied only resistance. In the third case, we will vary the load torque, and now we will see the effect. While changing the load torque, we will keep other quantity constant. So in the third case, suppose load torque is increased by 44%. Then what will be the new torque? It is third case, so I will represent it by T3. T plus 44% of T. So this will be 1.44 T. So load torque here is 1.44 T. Supply voltage is same. Resistance has not been changed, so R equal to 12.8 ohm. Load torque has increased. So I have just written that if load torque will increase, speed will decrease. So we will expect some value which is less than 800 rpm. Okay. Since the load torque has been changed, so in the steady state, machine torque will be equal to load torque, which will be 1.44 into previous torque. Again, if we write equation for machine torque, this is equation for machine torque, not for load torque. And why load torque is equal to this quantity? Because in steady state, load torque will be equal to electrical torque or the motor torque. Okay. Again here, phi is directly proportional to armature current, so we will write electrical torque is directly proportional to armature current square. So we will write TE3 divided by TE2 equal to, let's say IA3 is the armature current in third case, square divided by IA2 square. So from here we can write IA3 is equal to IA2 into root under T3 divided by TE2. What is IA2? IA2 equal to 5 ampere into TE3 is 1.44 T divided by T. Here we will get 5 into 1.2. In the third case, armature current is 6 ampere. There is one more quantity, armature voltage. What is armature voltage in this case? 195 volt. What is armature voltage here? 220 minus IA into R. 220 minus IA is 5 into 12.8. This will be 64. 20 minus 64 is, we have to find out the speed, and speed is dependent on armature voltage. So we will now write equation for armature voltage. Armature voltage is K phi into omega. Omega is directly proportional to speed, phi is directly proportional to armature current. So we can write EA is directly proportional to IA into speed. Now if we compare third case and second case, we will have EA3 divided by EA2 equal to IA3 into speed 3 divided by IA2 into speed 2. So EA3 will be EA2 into IA3 by IA2, or we'll write equation for N3 will be equal to IA2 into EA3 divided by EA2 into EA3 is unknown, but we can calculate from here. EA will be V minus IARA. IA is 6 and resistance is 12.8. This is 143.2. So N3 will be IA2 by IA3 means 5 by 6. EA3 divided by EA2. EA3 is 143.2 divided by EA2 is 156 into N2 is 800. This is 611.9 RPM. Okay, so here we have seen the effect of changing load torque. Okay, now we will make fourth case, and now we will try to observe the effect of supply voltage. Now suppose in fourth case, suppose we want to increase supply voltage such that the speed is brought to 800 RPM again. In fourth case we have speed equal to, we want speed equal to 800 RPM, and we are changing supply voltage. So V is unknown here. Since we are changing supply voltage, load torque has not been changed. So in the from first to second case, what we observed that if load torque is constant, the armature current will be same. So from third to fourth case, load torque is not been changed, so the armature current will be same. So here we will have armature current equal to 6 ampere. Load torque is same as third case. Resistance has also not been changed. We don't know EA here because we don't have supply voltage. If we talk about flux, flux is phi here. Flux is equal to, we know that flux is directly proportional to armature current in case of DC series machine. So in both the cases current is same, so flux will also be same. Now if we compare armature voltage from first case to second case, we will write equation for armature current. Armature current is equal to K phi into omega. So if you will write EA4, suppose in fourth case armature voltage is EA4 divided by EA3 will be K phi omega 4 divided by K phi into omega 3. and omega 4 by omega 3 will be n4 by n3. The both quantities are ratio of speed. Here we have taken speed in radian per second and here in rpm, but the ratio will be same. Okay, so this can be written as flux is same for both the cases. So this will be n4 by n3. n4 is 800 rpm divided by n3 is, this is 611.9. So from here we can easily calculate. See, in a problem you will be given with a situation, and by observing the situation, how fast you are able to recognize which quantity can be calculated easily. It depends upon your practice. If you have practiced more, you can easily recognize which quantity can be calculated very easily with the given situation. So initially when you will be solving this type of question, you will take some time, but when you will have practice, you will be easily able to solve this type of questions. So EA4 will be, EA3 is 143.2 volt. 143.2 into 800 divided by 611.9. This is 187.2 volt. Now you have armature voltage, you have current, and you have resistance. So V is equal to armature voltage plus IA into R. This is 187.2 volt plus IA is 6 ampere into resistance is 12.8 ohm. 264 volt. 264 volt. So this way we have seen the effect of change of resistance voltage, change of load torque, and change of supply voltage to a DC series motor. There is one way of controlling the speed of a DC series motor is by changing this resistance, and then another way is if we connect a resistance in parallel with the armature circuit or parallel with this field circuit or the coil, the speed can be controlled, and this resistance is called diverter. So I will take the same numerical value as we took in the previous question. Initially the speed was, in the first case when there is no diverter, in the first case we have speed equal to 1000 rpm, supply voltage 220 volt, armature current is 5 ampere without any diverter. We are using diverter only, load torque is not been changed. In the next case, okay, we have total resistance equal to, this is field resistance, and you can connect diverter in parallel with field resistance only, because the armature resistance is distributed in the armature winding. You cannot take out the armature resistance and connect a resistance parallel to the armature resistance. There are armature winding which are accommodated on the router, and the resistance is distributed in that winding only. So you cannot take out those resistance and connect a resistance parallel to that. So diverter can be connected in parallel with field resistance only. So there will be some armature resistance Ra, but for this case, or in most of the DC series machine, the field resistance, practically the field resistance is much greater than armature resistance. So even if you connect a resistance parallel to field resistance, the value of this combination will be much greater than armature resistance. So for this case, I am neglecting armature resistance. Suppose there is negligible armature resistance. Suppose we have field resistance equal to 5 ohm. Okay. In the next case, we have to find out a speed. Voltage equal to 220 volt. Torque is T. Field resistance is 5 ohm. This resistance of this winding has not been changed. Instead, a resistance parallel to this winding is connected. Now in the previous case, we observed that if in the two conditions load torque is constant, then in both the conditions armature current will be constant. But in the previous case, we didn't have diverter. What this diverter is doing here, for certain load, it needs some armature current. For example, in the first case, for certain load, to run that load at certain speed, the armature needs current. But if you will connect a diverter here, if you observe these two connections are in parallel. So if you will connect a resistance here, whatever current is entering here, that current will be divided equally if the resistance are same. The diverter resistance is also 5 ohm. So the armature current will be divided equally in these two resistances. If these resistances are not same, this armature current will be divided according to current division rule. Okay. So suppose in third case, let's say the armature current is IA dash. In the next case, suppose IA dash is flowing here. Or first, let's assume, as in case of previous case, what we observed, if torque is same, then I current will be same. If current is same, let's say again we have 5 ampere. So when there was no diverter, if you write formula for torque, we have K phi into IA. When there was no diverter, the flux was due to IA was 5 ampere and the whole 5 ampere current was flowing through the field resistance. So flux was also directly proportional to 5 ampere and we have torque is directly proportional to 5 into 5. In the case where we have diverter here, suppose the armature current is same as 5 ampere. We will again write new torque is equal to K phi into I. Let's say armature current is 5 ampere, but due to diverter, now flux will be due to, flux is due to only that part of current which is flowing in the coil. Here we don't have a coil, here we have a resistance. Although the resistance of this coil is also 5 ohm, but whatever amount of current flowing through this coil, we have flux. The flux will be only this part of current. Okay. So if we have 5 ampere here, we will have 2.5 ampere and 2.5 ampere. So IA is, in this formula, IA is 5 ampere. The new torque will be directly proportional to this 5 ampere, but flux is due to 2.5 ampere only. So now if you will compare the torque of previous case and torque of new case, these two torques are not equal. Okay, so to equate it, armature current has to be increased by some value, and there will be, due to increment of this current, torque will increase. Okay, so we cannot estimate from here. Let's say in the next case current is I dash. In the next case, let's say here we have current I dash. So what will be the current in field winding? This is 5, this is 5. Current will be equally divided. Now we will write torque is directly proportional to phi into armature current. We are neglecting saturation. So torque will be directly proportional to phi is due to, here the current will be Ia dash by 2, Ia dash by 2 into armature current is Ia dash, and the previous torque is directly proportional to previous current Ia square. And since the two torques are equal, so we will write Ia dash square by 2 is equal to Ia square. So Ia dash will be previous current root 2. This will be 5 root 2. And what will be the field current? Now if we want to calculate speed, speed is related to the formula of the armature voltage. We have K phi into omega. So let us first calculate armature voltage here. This is V minus Ia into R. So this was 195 volt. What will be EA in this case? 220 volt minus EA will be, this voltage will be supply voltage. Either you go by this loop or this loop. Both have same resistance and current. So what is the current here? Here the current is 5 by root 2. And in the previous case, the current was 5 ampere. Here we have 5 by root 2 into resistance is 5 ohm. This will be 202.32 volt. Okay, so now we have armature voltage in the two cases, and armature voltage is directly proportional to phi into omega, or phi into speed in RPM, or EA is directly proportional to, flux is directly proportional to field current or armature. Okay, let us first write field current into speed. So EA1 by EA2 is equal to field current in first case divided by field current in second case into N1 by N2. So N2 will be equal to EA1 by, N2 will be equal to EA2 by EA1 into IF1 by IF2 into N1. So EA2 is 202.32 divided by EA1 is 195 into IF1 is, the field current without diverter was 5 ampere, and due to diverter the new field current is 5 by root 2 into speed is 1000. 1467.3 rpm.